In this video, we want to take a look at this final box that we have on the last page of the notes. In this box are going to be some double integral properties. And remember that whenever we hear this kind of phrasing of a double integral, we should automatically be translating that in our mind to be volume under a surface. So these are really volume properties when we're working over a region D. Let's take a look here and see what the setup is, though, for all these 6 properties. The first thing that we have to recognize here is that we're starting with the assumption that the volume under F over D and the volume under G over D are both existing. Okay, so these double integrals both exist, and we'll also assume here that C is a constant. Well, if that's the case, the following 6 properties are definitely true. You'll actually note that a lot of these properties are very similar to what we have for like single integrals, like you would have seen back in a Calc 1 class. Take a look at these. This says here at the start, if you want the double integral of the 2 functions added together, that's the same thing as, well, doing the double integral of each function and adding the results together. So this should be very, very similar to a property that you saw in Calc 1. This held for single integrals. If you look here at property 2, this says if you have a formula f of xy and it's multiplied by a constant, you can take the constant and pull it out of the double integral. Again, very similar to what we know from Calc 1. Here's another simple property. This says if f of xy, if this landscape is kind of higher up, okay, if my f landscape is like up here, and my g landscape is a little bit below, it's not as high, and that's for every single point over which I'm integrating, then it should be the case that the double integral over f is bigger, or maybe the same, as the double integral over g. Now again, this shouldn't be surprising if I think about this as volumes. If f is the surface that is higher up, and g is a surface that is lower down, then it makes perfect sense that there's more volume under f than there would be under g. Property number 4 states that if you could rewrite D as kind of having, say, 2 different regions, like maybe here I imagine that my region D is like a circle, but I could like split it in half. So maybe the left half is like my D1, and my right half here is my D2. As long as that D1 and D2 don't overlap, they're kind of separate spaces, then you could easily do the following volume properties. Like if I wanted, say, the volume underneath F, so this like black landscape up here, over the entirety of D, that is the red and the green space combined, then of course it would make sense to find the volume over the red space and add up the volume that we would find over the green space, and then you would have found the volume over the entire circle. So again, all these properties should make a lot more sense if you're thinking about them as volume properties. The last 2 properties here are also really important. Property number 5, if we are looking for the area of D, and remember that's what we mean by this notation here, A of D. If I wanted, say, the area of this circle, then I could easily find that by just integrating the landscape of 1. And we talked about this actually in the last section with the very first example, where we said that if I was ever integrating the surface z equals 1 over any region, then what that would automatically tell me is the area of my region. Because again, I would go ahead and start by finding the area of that base, and then to find the volume under my landscape, I would simply go ahead and multiply by the corresponding height. And my height here would just be 1, since z is always 1. And so the volume that I get is actually equivalent to the amount of area that the region has. And so I can say here that this double integral will not only compute me the volume under the surface, but it will also compute me the area of D. Finally, we have here in property number 6 a way that we can make some nice estimations about volumes that might be difficult. And this again is very analogous to a property that you should have seen back in Calc 1. Okay, so this says, let's suppose that we have a surface f of xy, but maybe it's a complicated surface, okay? And maybe it's the case that we have a simpler surface, z equals little m and z equals capital M, that we could imagine as kind of sandwiching in our complex surface. If I was to draw, say, a picture of this, maybe I could draw something like the following. I could say I have a really messy looking landscape here, and I can imagine a plane that is larger than it, and I can also imagine a plane that is smaller than it down here. So I'll kind of color coordinate these. We'll imagine little m down here. We have our surface F in black, and we have our large surface up here of M. Now, if I was to just ask you intuitively, which one of these landscapes has the most volume underneath it, when we consider a region D down here in the XY plane, and I'll just draw something sort of like a square down there. Well, it would seem kind of obvious that the red surface, that capital M surface, should have the most volume. Little m would have the least amount of volume. And our surface of F in black would have kind of like a middle amount of volume. And if you look over at the side, that's exactly what we're stating over here. The volume underneath F of xy should be smaller than, notice, the area of D multiplied to that m height, so that would be the volume under m, and that should also be larger than the area of D multiplied by the volume, or by the height of little m. So again, if I view this as a volume property, it's pretty easy to see what it is that we're talking about. So these properties become super important to try to understand, because we use them from time to time to make comparisons, but also to make the evaluation of certain double integrals a bit easier.